In the preceding videos, we committed the power rule, the chain rule, and the product and quotient rules into our crib sheet of rules for calculating derivatives. In this video, we obtain the final set of rules in this slide deck by studying the derivatives of sine and cosine. We previously introduced the sine and cosine functions as descriptors of geometry, useful for talking about triangles and circles. These functions are also useful for describing oscillations in elastic materials in physics and in signaling networks with feedback in systems biology. Because triangles and circles are not necessarily obvious components of diagrams of vibrating piano strings or gene expression networks, we need alternative ways to sniff out whether a mathematical model is amenable to simple expression, or perhaps even solution, in terms of sinusoidal functions. The pattern that we will now describe serves as one such clue. The derivative of sine is cosine, and the derivative of cosine is negative sine. Roughly speaking, the sines and cosines have an interesting property, that they quickly come back to themselves, with occasional negative signs popping up, upon successive differentiation. We will now verify the rule for the derivative of sine. Here f labels the sine function with the association rule f on theta equals sine on theta. Substitute this association rule into the definition of the derivative. df d theta equals the limit as delta theta approaches 0 of the fraction, with numerator sine on theta naught plus delta theta minus sine on theta naught over the denominator delta theta. Using the angle addition identity for sine we previously reviewed in the video on trigonometry, we rewrite sine on theta naught plus delta theta using the mnemonic sine cosine cosine sine, or more slowly sine on theta naught times cosine of delta theta plus cosine of theta naught in yellow times sine on delta theta in yellow. Everything else in the equation is untouched. Collect the terms formatted in white font in the numerator so that they read sine on theta naught times quantity cosine of delta theta minus 1. Now split the limit into two pieces, the limit as delta theta approaches 0 of sine of theta naught times the ratio of cosine of delta theta minus 1 over delta theta, and the limit as delta theta approaches 0 of cosine of theta naught times the ratio of sine of delta theta over delta theta. To investigate the behavior of sine of delta theta and cosine of delta theta as delta theta becomes very small, we draw a flattened right triangle with hypotenuse of length 1, meaning a triangle embedded in a unit circle. We indicate an arc length delta theta. The length of the leg opposite the turquoise labeled angle of delta theta is sine of delta theta. As delta theta becomes arbitrarily small, meaning as the triangle becomes arbitrarily squashed and flattened, the length sine of delta theta and the arc length delta theta become arbitrarily close to each other. The ratio sine of delta theta over delta theta goes to 1. The length of the leg adjacent to the turquoise labeled angle of delta theta is cosine of delta theta. Since this leg does not quite reach far enough out from the center of the unit circle to touch the circle's edge, there is a gap of length 1 minus cosine of delta theta so tiny that we need to highlight it by animating an arrow. As delta theta becomes arbitrarily small, meaning as the big turquoise triangle becomes arbitrarily flattened, the length 1 minus cosine of delta theta in green becomes arbitrarily small relative to the arc length delta theta in orange. The ratio cosine of delta theta minus 1 over delta theta goes to 0. Thus, df d theta at theta equals theta naught equals cosine of theta naught. The derivative of sine is cosine as expected. To develop visual intuition for the idea that the slope of sine is cosine, we compare the plots of sine of theta versus theta and cosine of theta versus theta. According to the equation that we have just derived, the slope of the turquoise curve and the height of the golden curve should be equal. Pay special attention to see whether this is true as we move around the unit circle. Wherever the turquoise curve is steep and climbing, the height of the golden curve should be positive. Where the turquoise curve is descending, the height of the golden curve should be negative. And when the turquoise curve passes through a peak or a trough, the golden curve should pass through 0. Were you able to confirm the expected behavior? In the same way as we compared the slope of the turquoise curve to the height of the golden curve, we can also compare the slope of the golden curve to the height of the turquoise curve. Are these equal? Are they different? Please pause the video to determine the relationship. Now that you have paused the video and studied this slide, you have certainly made the following observations. When the slope of the plot of cosine is positive, the height of the plot of sine is negative. When the slope of the plot of cosine is negative, the height of the plot of sine is positive. And when the plot of cosine is flat, the height of the plot of sine is 0. These observations are consistent with the rule for the derivative of cosine that we mentioned at the beginning of this video. We claimed that the derivative of cosine is negative sine. Because we have already invested effort into calculating the derivative of sine, we can quickly confirm the rule for the derivative of cosine. The solution is left to you, the viewer. Here's a hint for beginning a response. Consider the right triangle with angle theta, which is just as well specified by indicating that the opposite angle is pi over 2 minus theta. The leg that is adjacent to the label for theta is also the leg that is opposite the label for pi over 2 minus theta. Hence, cosine of theta equals sine of pi over 2 minus theta. The leg that is opposite the label for theta is also the leg that is adjacent to the label for pi over 2 minus theta. Hence, sine of theta equals cosine of pi over 2 minus theta. You may check the plausibility of these identities using the plots of sine and cosine versus theta on the preceding slide. Please pause the video to use these identities, along with the rule for calculating the derivative of sine, to confirm that the derivative of cosine is negative sine. Derivative of sine is cosine and derivative of cosine is negative sine. Together, the analyses you have followed and, in some cases independently performed, using this video, show that derivatives of sinusoidal functions are sinusoidal functions themselves. The derivatives of sine and cosine on this slide display a pattern that we will point out by reading out font colors. Derivative of white equals yellow and derivative of yellow equals negative white. This fashion in which white and yellow provide each other's derivatives, with a negative sign in the second equation, is a hallmark of dynamical systems in which oscillations might be supported. We will revisit this point in the chapter on differential equations. In this slide deck, we defined the derivative and carefully described differentials, and then built up a small crib sheet of rules for calculating derivatives when working with power law functions, composite functions, products and quotients of functions, and in this most recent video, sinusoidal functions. It is important to be comfortable working with derivatives, because derivatives are often used as basic vocabulary for specifying the details of dynamical systems. These include cell populations and the abundances of biological molecules inside cells.